If your MESA Ethernet card is giving you following errors or an error finishing read, the problem isn't your hardware, it's your kernel configuration. I'm going to show you undocumented techniques that reduce latency to near zero by using advanced kernel tuning techniques. This works on Debian Trixie with the preempt RT real-time kernel, and we're going to cover 5 critical optimizations nobody else knows about. And at the end, you'll run a 60-second stress test proving your setup is rock solid. With a MESA card, LinuxCNC runs a single real-time thread, the servo thread, that fires every millisecond. That's 1,000 times a second. In my testing, I observed the real-time thread took about 200 microseconds, or about 0.2 of a millisecond, to execute, and then it sleeps until it's due to fire again. If excessive latency or jitter occurs, the execution time could exceed the available time, which on MESA cards causes the dreaded error finishing read, which disables all communication to the card for safety until the MESA card is reset or LinuxCNC restarted. So what is jitter? Imagine you're the drummer in a band and it's your job to bang the drum every 1 second. Sometimes you'll be a little bit late, other times you'll hit the drum early. If you graph those differences in your timing being away from the 1 second target, you might end up with a graph like this, which is the jitter on the servo thread recorded on a LinuxCNC installation. Network latency also needs to be considered. It's important that the servo thread process never exceeds the time slice due to these jitter spikes. So what's an interrupt or IRQ? A computer interrupt is a signal sent to the CPU to temporarily pause its current execution and immediately handle a higher priority event such as a key press on the keyboard or data arriving on a network card. An IRQ, an interrupt request, is the traditional hardware mechanism used on x86 systems to deliver these interrupts. Each device is designed a unique IRQ number, and when an interrupt occurs, it's serviced by an interrupt service routine or ISR for that IRQ before the interrupted program is resumed. Why does this matter? Standard Linux kernels often batch network interrupts together to save power, and this is death for real-time tasks like LinuxCNC because CNC motion cannot run late. So we're going to implement some super secret real-time kernel optimizations to make sure this never happens. There's a couple of ways to change kernel settings, but I like to use Grub Optimizer, and where I've got to edit text, I use the Genie text editor. So let's install them. Sudo apt install Grub Customizer. So it's time to check what our network driver is and to see if there's any special things that we have to do to support it. IRQ coalescing groups interrupts together, which is great for web browsing but terrible for real-time CNC. So instead of responding to each packet immediately, the network interface card waits to batch them to save power. So if we type in, we'll check support, we can type in sudo ethtool -c enp0s25, and when we get that output on the screen, we can see that RxUsex has a value here, so we do need to sort something out with this. So if we go to sudo genie etc network interfaces, we can edit this, and we need to put in ENP0S25, ENP0S25. So we need to set some settings here for this network card. ENP0S25, ENP0S25. And you can find this information is actually, you can, if you type in man hm2_eth, which is some of the Linux CNC documentation, if you scroll down here, it will show you what has to be put in and also the file that you need to edit. So just do it by the numbers and use the documentation. Is to disable energy efficient Ethernet. And this is a technology that shuts down the network from time to time to save energy. And we can't afford that because it takes time to sleep, to wake up the Ethernet card from sleep. So there are ways to simply do this in our system, but it's not robust because each Ethernet card model can have different settings in it. So we're going to do a more robust solution. So we're going to we're going to create a service. So sudo genie etc. systemd system disable EEE service. The other advice that you get is to install cpupower, and that's also no longer available in Debian Trixie. So the reason why this file is used is to actually install or set the CPU governor to performance. Once again, this is a file that we can delete. So we can go sudo opt purge cpupower, and also then what we can do is use in its place CPU power. So we can go sudo install Linux CPU power apt install, sorry. So once that's installed, all we need to do is sudo CPU power frequency set the governor to performance. I've got a tipping spelling error here. So now we get to the secret source of this, and that's how to pin the Ethernet interrupt request to the same isolated CPU as what we're using for Linux CNC. So why is this critical? Network drivers in Linux are never real time, so because we've isolated a CPU in LinuxCNC, we need to force network interrupts to be the same core to prevent delays. So we're eliminating the interrupt latency from other system processes. So we need to first find our IRQ number, grep ENP0 S25 and / pros interrupts. And there we have it. We've got ENP0 S25 here, and we're showing it here as a interrupt IRQ request of 25. So now we just want to talk about what this is. We've got 8 CPUs numbered 0 to 7, and in a hexadecimal world we need to, we'll start with a binary. In the binary world we need to have a bit mask. So if we're looking at this one here of being core number 7, we need to have a 1, 4, 5, 6, 7. So that's the 8th bit. 1, 2, 3, 4, 5, 6, 7, 8. So we need 8 bits in our mask. And that actually, if we convert that to hexadecimal, which is base 16 instead of base 2, we ended up with 80. So being 1, 0, 0, 0, 0, 0, 0. So there's the 8 and the 0. So we know that we've got to put 80 into our thing. So if we go to echo 80 to sudo t to pros IRQ 25 SMP affinity. And then if we cat that just to list the contents, we've got 80 there. So I had a little bit of trouble sorting this out because it wasn't clear in a lot of the documentation that I was reading that they were hexadecimal numbers, and I couldn't work out why I couldn't enter decimal 128 into this file. It generated an error, so there's some error checking in it. I think we've now solved everything. So what we should do now is to do a reboot to make sure we've got everything working fine. Sudo reboot now. One of the things you might hear about when you check other articles about preempt RT tuning, you might find mention to IRQ balance. Now, IRQ balance is an obsolete system now, and you should not install it. What it used to do is go through your interrupts, your IRQs from time to time, and balance them out against various across the various CPUs. So the kernel now does that internally, and there's no need to do it. And in fact, it may impede in performance and increase latency spikes as it runs. So IRQ balance no longer exists, so don't use it. We did talk about having to deal with Realtek network cards, and the problem we've got here is the default Linux network driver for them is very poor quality and is high latency and totally not suited for a real-time environment. So I will show you on another computer what this looks like. So let's have a look for a Realtek card. If we run that lsshow command, lsshow -class network, you'll see that this computer has two network cards installed. One is an Intel card with the name of ENO1, and the other one is a Realtek RTL8125. So this one here needs some tender care. Now, one of the things that we need to double check is that the drivers are in the Debian non-free section, which is not installed by default. So if we go through to etc. apt sources list D and find Debian sources, you'll find here that here under stable or Trixie, we've got these sections here: main, non-free firmware, which is the two default ones, and non-free needs to be added. So if we're going to get these drivers, we need to add non-free here and then do the sudo apt update. So this is okay, we've already done it, so that's good. So just remember to check that non-free is here. So now what we can do is now we know that's installed. We need to sudo apt install dkms, which is required as a dependency. It's already installed. And now it's an 8125 driver we've got, so we can install the R8125-DKMS driver. We've already installed this, which is good. And we might have a look at, if you just in a browser type in Debian packages search, and if we can search for I want to type in R8125 DKMS here, R8125 DKMS, and if we open this up, it'll tell you what it's installed for, so what it's ready to use for. And the other thing that we might want to look at is the R8168 is the one. So this driver here, the R8168 DKMS, is applicable for a large number of cards, network cards, and it's probably the most popular one that I've seen is the RTL8111. And there's various variations of it, but if your Realtek network driver is in this list, you need to go back to sudo 8 and type in 8168 here. So once you get that installed, there's nothing else that you need to do to make this real-time ready, network real-time ready. So now we've completed and covered every option that I know of that you could encounter that will impact on your real-time performance. So it's time to do some tests. So let's see what happens. The one that we use with LinuxCNC is LinuxCNC's latency test. I use latency histogram, but there is a simpler under the CNC menu. There's a simpler latency test here, which shows performance for a servo thread and the base thread. So the servo thread is being tested at a millisecond, and the base thread's being tested at 25 microseconds. So a lot faster. And this one is used for software stepping of stepper motors. But if we type this option, which is not in the the menus, if you type in latency-histogram --no base, so we're not going to look at the base thread, --sbins 1000 --show. Now, what this says is the sbins will draw a histogram with 9 lines, with 1,000 lines, and show will show anything that falls outside of the actual graph. So let's run that. Here we go. The maximum test time is 4.7 at this point. We can add a little bit of a load to it by loading some of these things called GLX gears. So I probably wouldn't normally go past 8 of them. Also, it's recommended that you abuse your computer and run a few YouTube videos, and finally, so that you've got the ability to check this against history, you can take a screenshot and save it in a folder. So we're seeing here that actually hit a latency spike just saving that. So we're now sitting at 6.3 microseconds per is the jitter. So that's really very, very strong. People are doing this from a non-Linux CNC background. You're probably more accustomed to using real-time tests. So the other alternative is sudo apt install rt-tests, which I think is already installed. So it's already there. But now we've installed that, we can type in sudo Cyclctest. Loop 1,000 times. Probably would need to do 60,000 to be similar to what we're doing. And 1 core with a priority of 99. So we're only going to run this for 1,000 runs, so it didn't take very long, but you can see here now you get the hang of it. The minimum reading was 2 microseconds. The average, the actual there was 3, and the average for that was 2 across those 1,000, but the maximum was 8. So that's your jitter test. So normally you'd run that for a lot longer, maybe 60,000. Now, this is the one we've all been waiting for, is how to test the network latency. And to do that, we use the ping command. So we can type in sudo chrt 99, priority 99, ping is the command we want to run, -i 0.001. So run this every microsecond or every 0.001 milliseconds. Do it quietly, I'd say just report at the end, and run it for 60,000. So 60,000 will take 1 minute to run. And we need to type in the address of your MESA Ethernet card. Now, I don't have a MESA Ethernet card on this system, so I'm just going to pick another PC on the network. And it'll sit here for 60 seconds. So there we go. The minimum is for 0.095 of a millisecond. The average is 0.146, and the maximum, which is probably the first packet as this started, was 0.316, and the range there is 0.013 of a millisecond. So what's good? So good is somewhere less than half a millisecond. I'd like to see a little bit less than that, but at least less than half a millisecond, and a deviation of not much more than what we're seeing there. So, and a bad one will see the average to be up around or a little bit under 1 millisecond. So let's have a look at this 0.146. So 0.146 of a millisecond plus what I said, 0.2 of a millisecond. That's 0.346 of a millisecond of time that's been used. So a bit of jitter, we saw, say, I'll call it 10. So plus or minus 10. So about 0.36. So we've got nearly about 0.66 of a millisecond to handle any jitter, even though that we've allowed for it. So if there's something happening that we don't know about, then it shouldn't impact anywhere on this. So we're happy at that. So in conclusion, let's recap on what we've done. We've set the grub kernel parameters correctly. We've set the CPU governor to performance. We've got our IRQ coalescing disabled on the network. We showed you how to install the correct network driver if you've got a Realtek card. And we've got the CPU core that's running LinuxCNC, core 7 on this PC, has been isolated, so it's not used by anything else. And we have our Ethernet IRQ for the network card in use pinned to that isolated CPU, so it's nice and close, so there's no latency as things swap from one CPU to another. And we've verified that we've got very good acceptable network latency, and I would expect to see much better performance on a MESA card in a real-time environment than just a sloppy test across a network that is not real-time and I think has another little router between the two PCs. So from here, run this 60-second test and post your latency in your maximum latency and your figures. Post them in the comments below so I can see them, because I'll be very interested to see what you can receive. And I'll add some configs to a thread in on the LinuxCNC forum, and that will help you configure some of these files. And keep an eye out for my next video, and also check out my previous videos, because this is the third video that I've done that is about configuring Debian Trixie for maximum performance for LinuxCNC. So see you in the next video.